Hello, in this video we are going to discuss about the radioactivity. This is standard 10 ICSE syllabus chapter. I am going to restrict this lecture till grade 10 only. So let's start with the radioactivity part. So first of all, you must understand that radioactivity is a nuclear phenomenon. So everything associated with radioactivity is happening from within the nucleus. So we are going to just compare the atom and nucleus volume wise, right? Because that is the beginning of the chapter. So here I have tried to explain the volume of atom and nucleus with respect to a playground, cricket playground. So just imagine that this is the pitch of the cricket stadium, and at the center of the pitch you have a very small ball. So this is the cricket ball which is placed at the center of the cricket pitch. And now you can consider this ball to be the nucleus and the entire stadium to be the atom. So almost the volume of the nucleus is 10,000 times less than the volume of the entire stadium. This is just a comparison. So a lot of empty space is there in the atom, and only a very small section of the entire volume is being occupied by the nucleus. So that is what I have mentioned over here, that about 99.9% is occupied by the electrons and the empty space, right? Rest everything is the very small section is being occupied by the nucleus. Now there are few common terms like atomic number, mass number, isotopes, isobar, and isotones. So atomic number, first of all, it is the number of protons. So most of the students, they get confused that the number of electrons is the atomic number, but please understand that atomic number is the number of protons in an atom. The number of electrons and protons are same. But when you are discussing about ions, say for example copper plus 2, then copper plus 1, and then you have an atom of copper, then the atomic number is same for all of these three, because the atomic number is the number of protons, and the number of protons in all of them are the same. You might remove 1 or 2 electrons to make the ions, but the atomic number stays the same. Mass number is the total number of protons and neutrons inside the nucleus of an atom. So the sum total number of protons and neutrons is represented by A, that is the mass number, and atomic number is represented by Z. So moving next, isotopes. Now isotopes are the atoms of same element which have same number of protons but different number of neutrons, or same atomic number but different mass number. So here carbon 6, again carbon 6, but atomic number same 666, but the mass number 12, 13, and 14. Now these three atoms are already present in a piece of carbon. Suppose you take any piece of graphite or anything which is made up of carbon, all these three isotopes are going to be there. But percentage wise, C12 is found comparatively larger than the other two, right? Now you can see that their mass numbers 12, 13, and 14 are different, but the atomic number stays the same. So if the atomic number is same, the element remains the same. So these three are the atoms of same element. But now if you subtract 12 and 6, you will get the number of neutrons. So here 6 neutrons, here 7 neutrons, and here 8 neutrons. Moving ahead, isobars. Now isobars are actually the atoms of two different elements. So say argon and calcium. They have same mass number, but their atomic numbers are different. So argon has atomic number 18 and calcium has atomic number 20. So atomic numbers are different, but the mass numbers are the same. Moving ahead, isotones. Isotones means you may have many nuclei of different elements which have same number of neutrons. So here I have given two such examples, calcium and potassium. So if you subtract mass number and atomic number, in this case 39 minus 19, you will get 20. 40 minus 20, you will get 20, which is the number of neutrons. So if the number of neutrons remains the same, they are known as isotopes. All right. So now in case of radioactivity, the entire credit goes to these two people, Madame Marie Curie as well as Henry Becquerel. Now there is a long story behind the discovery of radioactivity. We shall not go into that much detail, but just a glimpses. If you want to know more about Marie Curie, then there is a very good movie named Radioactive. So the entire life of Madame Marie Curie is being depicted in form of this movie. You can very well see that, right? And Henry Becquerel, once he was doing an experiment with potassium uranyl sulfate, then that compound was having uranium in it, which is radioactive. Now, after completion of his daily lab work, he just wrapped that salt into the black paper and kept it inside his drawer. And he was not knowing that there is a photographic plate which is packed inside and well placed inside the drawer. On the very next day, when he opened up the photographic plate, and it was new brand photographic plate meaning you can understand that the rolls which used to come in the camera before 10-15 years, that one, right? But if you just open up that roll into this visible light, it is going to get damaged, exposed and finished. You can't use it again. So the photographic plate, it was brand new, kept inside the drawer without any kind of interaction of light, got damaged. Then he thought that some mysterious rays might have come out from this sample, salt sample. It would have passed through this black paper and it would have passed through the photographic plate and make them damaged. From this was the actual beginning of the radioactivity. So Madame Marie Curie is the only one lady who received 2 Nobel Prizes in physics and chemistry, and that particular Nobel Prize was actually in sharing with Henry Becquerel for the discovery of radioactivity. Marie Curie also discovered radium and polonium, also studied its characteristics, and the office of Marie Curie is today known as Radium Institute, which is in Paris. So let's go ahead. If you look at this periodic table, then we have mostly those elements which are radioactive whose atomic number is greater than 83. In ICSE textbooks, they have mentioned greater than 82, but with respect to 12th standard textbook, 83 is the atomic number after which mostly these elements become radioactive. So you can say that these elements, and not this first series, the actinide series, most of these are radioactive. Now we take an example of uranium 92-235. So there are 92 protons, and if you subtract 235 and 92, you get 143 neutrons. You can see that the number of neutrons is very large compared to the number of protons. So in nuclear physics, we consider those kind of elements to be unstable. An unstable element from its nuclei releases alpha, beta and gamma radiations and becomes stable. So first of all, you should understand that why these are radioactive. So I am just restricting this lecture till 10th grade because this nuclear physics is a very vast topic beyond our understanding also. So just try to understand a little bit about radioactivity in this way, that those nuclei in which the number of neutrons is more than that the number of protons, mostly after atomic number greater than 83 or 82, are radioactive in nature. Now, some basic important points about the radioactivity, we need to understand it. So this is the definition of radioactivity: spontaneous emission of invisible radiations, and radiations are of 3 types: alpha, beta and gamma, from the nuclei of the unstable element. I have already told you what an unstable nuclei means, and that is why we have made a statement in the second point that it is a nuclear phenomenon. It is associated with only nucleus. It has to do nothing with the electrons which are moving in the orbits. So the electrons which are moving round and round about the nucleus has no role in radioactivity. So all these radiations, they come from within the nucleus, the alpha, the beta and the gamma. Right? Now let us understand point number 1. So this is what I have explained you, that suppose this is the nucleus and these are the orbits, these are the electrons which are moving in the orbits, but these do not have any role in the radioactivity. Any kind of alpha or beta or gamma emission takes place from within the nucleus. So that's why we have given the name as nuclear phenomenon. I will come back to this temperature and pressure and chemical action part. Let us discuss the third point. Spontaneous means naturally by itself. We do not induce radioactivity. We can't say that, okay, nucleus, come on, start emitting radiations. It doesn't happen that way. If a nucleus is radioactivity, if a nucleus is radioactive, then it is going to emit radiations by its own. You cannot stop that radiations by heating, by adding any kind of chemicals on it, by making a chemical reaction with that radioactive element. Nothing is going to stop the radiations. That is what I'm going to come up. So naturally by itself means we don't give instructions that, okay, nucleus, start emitting the radiations. It happens by its own in nature. So the radioactive substances, they do not wait for anybody's permission. Their nuclei themselves, they start emitting the alpha, beta and gamma radiations by themselves. So it is a natural phenomenon by itself. We don't induce we humans do not induce the radioactive phenomenon. Now, let us understand the second point in detail, that why any kind of chemical action or temperature, pressure doesn't affect the radioactivity. So suppose if I say that chlorine forms bond with chlorine. So we know that there are electrons, and those electrons, they keep on sharing, and finally the covalent bond is formed, and then the reaction takes place, right? This is what happens in the chemical bonding. The electrons in the outermost orbit, they take part. So suppose if you combine uranium with oxygen, you are expecting uranium oxide to be formed. That's perfectly fine. But in those uranium oxide reactions, the electrons in the outermost shell are going to take place, whereas the radiations, they come from the nucleus of the uranium. So here, suppose this is uranium nuclei, here this is oxygen nuclei, then there is a electron transfer or electron sharing between these two atoms. But the alpha, beta and gamma radiations, they come from within the nucleus, and during the chemical reaction, the nucleus remains unaffected. So it still remains radioactive. Got that? Fine. So radioactivity, even if after the formation of uranium oxide, radioactivity still remains. The next point, if you keep on heating or if you freeze the radioactive substance, the nuclear radiations are still going to come out. No effect. If you do any chemical reactions or pour acid, no effect. Radiations are going to come out. Random phenomenon. Now, random phenomenon means that suppose you have a piece of uranium, say 92 to 35, and you have 50 grams of uranium. Now, if you explore the half-life, there is something called a half-life, then you will see that these half-life of these radioactive elements are in thousands of years. So I'm just assuming a number, say 1,000 years. Actually, it is more than that. Radioactive half-life of uranium is, suppose, 1,000 years. That means from 50 grams, disintegration, after disintegration takes place, it becomes 25 grams, and it takes 1,000 years. From 25 to again 12.5 years, it's half, it will again take next 1,000 years. In next 1,000 years, it will disintegrate into its half, that means 6.25. So you can very well understand that as the disintegration process starts, it becomes even more slower. Now, I know that this is not going inside your head. I'll explain it very clearly to you. So let's come back to uranium 50 grams. You have these uranium atoms, and to be very specific, I will not discuss now atoms. I will just say that these are all uranium nuclei. And you can very well find out the number of this uranium nuclei with the help of mole concept, right? So say 235 grams is equal to Avogadro number, then 50 gram is equal to what? So these many nuclei, now which nuclei is going to emit what at what time? We can't say. So suppose this nuclei emits alpha particle, this emits beta particle, this might be emitting gamma radiations, but this nuclei might not do anything for next 10 years also. So it is highly unpredictable. We can't say that it is going to emit alpha or beta or gamma or such kind of radiations. Any nuclei can emit whatsoever radiations at its own time. Correct? So it is highly unpredictable phenomenon. We can't say which nuclei is going to emit what at what time. Now, at a time, a single nuclei can emit only one radiation. Either it can emit alpha or it can emit beta or gamma, right? It may happen that after the emission of alpha particle, it may again emit alpha. It may happen that an element or a nuclei might be emitting beta radiations and it is still emitting beta radiations even after the new element is formed. So suppose one time beta emission took place, it may happen, it may emit alpha or beta or gamma, anything, we can't predict. But final product should become stable, and when I say stable, it does not mean stability through octet or duplet rule. We will understand the process of alpha and beta and gamma emission in detail. So this is what is random phenomenon. We can't say which nuclei is going to emit what at what time. Correct? Now, just talking about this half-life, which is still not there in the syllabus, but you need to understand this, that it will keep on radiating the radiation still thousands of years. So suppose there is a radioactive disaster that took place at one area, say Fukushima in Japan, or the Chernobyl nuclear reactor blast from 1986. Now those radioactive dust is now mingled with the soil and everything. So that zone is going to remain radioactive for next thousands of years. Correct? So humans can't stay in those radioactive zones because those radiations are harmful to human beings. Moving ahead, the alpha emission. Now you should understand that alpha particle is basically a helium nuclei. Alpha particle is made up of 2 protons and 2 neutrons. So its charge is going to be plus 2e, because charge on a single proton is 1.6 into 10 raised to minus 19, which we represent it by e. Neutrons don't have any charge, so this is the charge of the alpha particle. Now, why do we call alpha particle as helium nuclei? Because 2 protons, 2 neutrons, and then you have 2 electrons which are there in the orbit of the helium atom. So these are 2 electrons. Suppose if I rip away these 2 electrons, I'll be only getting the helium nuclei, which is nothing but 2 protons and 2 neutrons. So that's why we say that alpha particle is a helium nuclei. Now, let us understand that if uranium atom emits alpha particle, what is going to happen? So I'm going to represent this U as X, atomic number 92 as Z, and then 235 mass number as A. Now, since it is emitting alpha particle, minus because the alpha particle gets removed. Correct? So I'm going to say alpha particle as 2He4. Please do not write down plus 2 over here. We understand that we are only going to talk about the nucleus. Again, alpha particle is written as 2He4. Now, very simple, Z minus 2. So you have Z minus 2. Then you have A minus 4. So I'm going to write down A minus 4, which means a new element is formed. You can very well see that Z minus 2 means an element with atomic number less than Z. So if the atomic number changes, that means the element itself changes. Now this is known as parent nuclei. Parent nuclei is the one which is radioactive. This one is radioactive. So after emission of alpha particle, it changes into a new element, say Y, with atomic number 2 less and mass number 4 less. And this is known as daughter nuclei. Correct? Like this. So here 92 minus 2, so 90, and 235 minus 4, so it is 231. And basically this is thorium, but you might not want to remember this because periodic tables can't be remembered by all, right? So this is one example. If you are able to mug up, then fine, or else simply leave it. Let us understand that how did this take place. So suppose this is a uranium nuclei which was having 92 protons and 235 is the mass number, that is I am writing A, and 143 neutrons. So out of these 92 protons, 2 protons are now gone. And out of these 143 neutrons, 2 neutrons are gone, which means this nuclei has emitted an alpha particle like this. So now in this nucleus, there are only 90 protons which are remaining and 141 neutrons that are remaining. So the mass number is the sum of protons and neutrons that decreases by 4. And since 2 protons have left the nuclei, the atomic number decreases by 2. So that's why this is how simply you can remember this one. Simply Z minus 2. So Z minus 2, A minus 4. I'll just highlight this and show it to you. Z minus 2. So here Z minus 2. A minus 4. So here A minus 4. So the daughter nuclei has mass number 4 less than the parent and 2 atomic number less than the parent. Some properties of the alpha particles are that its speed is roughly 10 raised to 7 meters per second. Its mass is about the rest mass, that means when it is not in motion, its mass is almost 4 times that of the proton, because alpha particle is made up of 2 protons and 2 neutrons. And we consider the protons and neutrons to be of same masses. Ideally, a neutron is heavier than the proton, but still, that's okay at your level. It has positive charge because it contains 2 protons. Neutrons, they don't have any charge, right? Specific charge is charge to mass ratio. So how it can be calculated is, it has charge 2 into 1.6 into 10 raised to minus 19 coulomb divided by mass is 4 times the mass of the proton or neutron, that is 1.67 into 10 raised to minus 27 kilogram. So SI unit would be coulomb upon kilogram, and very well calculate this and you will get this answer. Since it is a particle and not the wave at this moment of time, so we don't want to calculate its wavelength. Now, it deflects towards the negative charge because it itself is positive. So it would want to go towards the positive plate. We will discuss about that. The ionizing power of the alpha particle is the maximum. So what do you mean by ionizing power? Let us understand that. Suppose this is a nuclei and these are the electrons and this is the electron in the outermost orbit. So this becomes an atom. Now when you bombard the alpha particle on this atom, this alpha particle is going to hit this electron and this electron will be knocked off from its orbit and the alpha particle itself will go away. So this atom, which was atom, now it has 1 electron less because the alpha particle has ripped away one of the electrons from its outermost orbit, which makes this atom be a positive ion. So a positive ion is formed as a result of this collision of alpha particle with the electron in the outermost orbit, and that is why we call this process as ionization. So compared to beta and gamma radiation, the alpha particle is 1,000 times, almost 10,000 times more ionizing capacity. So almost we can say that the ionizing power of alpha particles in comparison to beta and gamma is 10,000 times more, highest ionizing power. When it comes to penetrating power, it is very less. It can go maximum till about 3 to 8 centimeters in the air. Then after it is going to lose its kinetic energy, right? Now, since it cannot go to a very large distances, even a very thin piece of paper is able to stop this alpha particle. Now, since it cannot penetrate inside the human body, so it actually damages our body very, very little. Next few properties, like it produces fluorescence. Now, you might have already studied this alpha particle scattering experiment by Rutherford. Then this is the gold foil. So when alpha particles, they are being bombarded, these are the alpha particles and this is the radioactive source. So the alpha particles, they actually hit this gold foil and get scattered in all the directions. So this is one of the properties, that the alpha particles can be scattered by the gold foil, and when it hits this fluorescent screen, it glows, it produces fluorescence. So that is again a next characteristic, that alpha particles, they produces fluorescence when it is being acted upon or when it hits the fluorescent screen. So now let's discuss about the beta emission or the beta particle, how it is going to release from the nuclei of a radioactive atom. So first of all, you need to understand that beta particle is represented by this sign, and in grade 12 you will understand that beta particle can be beta plus, that is positron, and beta minus, that's an electron. So basically positrons are the particles having charge opposite to that of the electron and they have same mass as that of the electron. But we are not going to discuss about the emission of positron over here. In grade 10 we always discuss about the beta minus emission. So this one. So first of all, we need to understand that since this is an electron, how can electron they can be released from the nucleus of an atom. So let's understand that. This is a nuclei. X is an element, Z is the number of protons. So there are Z number of protons over here, and A minus Z, that is mass number minus the atomic number. Now let's understand how to write down the neutron. So this is neutron symbol N. We write the charge at the bottom part, and the mass of the neutron is written over here at the top. Now this neutron breaks up into a proton. So charge of proton +1, and the mass is also 1 unit. So I should write down 1 at the top. Now since all the nuclear reactions they obey the law of conservation of charge, so the total charge on left hand side must be equal to total charge on the right hand side. So here we have 0 charge. Now since there is a positive charge over here, so there should be a particle with negative similar charge produced, and that is an electron having almost 0 mass. So plus we do have something called antineutrino. Now you need to understand that when one neutron breaks up into a proton and an electron, this electron produced is within the nucleus. Now since electron is a negatively charged particle and it cannot stay inside the nucleus, so it is ejected out of the nucleus, and that electron is itself known as beta minus particle. So if a neutron breaks up into a proton and an electron, then that electron which is produced inside the nucleus due to the breakage of the uh, neutron, that is known as beta minus particle, and it is ejected out. Now since this antineutrino, it is actually a chargeless and massless particle, but it has a very negligible mass, and the scientists they actually had to keep this particle because the law of conservation of momentum was not followed. But again in grade 10 we are not going to discuss about this as well. So what is our learning outcome from here? That there is one mass number which is going to decrease, but simultaneously since there is one proton which is produced, so the mass number remains as it is. Please understand this, that if one neutron gets less, then one proton also increases in number. So the mass number is the sum of protons and neutrons. So there is no change in the mass number, no change in mass number in going from the parent nuclei to the daughter nuclei. So I'm going to give you one example as well. And then since there is one extra proton produced, so the one atomic number increases by 1. Like this. So let's write it down in a very proper manner. So suppose we have X, Z, A, and if it releases, so minus beta particle like this, and beta particle is an electron with negative charge at the bottom, and the mass is almost 0. So now it is going to produce another element. So Z minus 1 like this is Z plus 1, A minus 0, so it is A. So please understand that earlier you had X, Z, A, So the number of neutrons, the mass number was A, and the number of neutrons was A minus Z, and Z were the number of protons. Now, since one proton has increased, so the atomic number increases by 1, but there is no change in the mass number because one less neutron but one proton got added up. So the mass number also remains the same, like this one, right? This was A minus Z, the number of neutrons. Now here the number of neutrons would be one less, so it would be A minus Z minus 1, correct? But there is no change in the mass number, right? So suppose if I would want to give you the example of uranium, suppose this is uranium 92 235, and if it releases beta particle, then I should be writing this as 92 minus 1, so 93, 235 minus 0, so 235. Whatever it may be element, simply write down this as Y. And you can observe one more thing, that this was the parent nuclei, and this is the daughter nuclei. You can see very well that the mass numbers are the same. So basically these two are isobars. So whenever there is a release of an beta minus particle, so isobars are being produced, right? So now let's talk about the properties of the beta particles. Nature, they are negatively charged and they are energetic electrons, since they are being produced by the breakage of neutron into protons as well as the electrons, right? The speed is almost 90% as that of the speed of light. The rest mass is very, very negligible. Just understand that if had it been this particle would be at rest, then as per the Albert Einstein's relationship of the rest mass, right, that comes out from the theory of relativity, we don't need to go into that much of the detail, but its mass is negligible. The charge is negative, and of course it is minus 1.6 into 10 raised to minus 19 coulomb. Charge is to mass ratio can be found out very easily because we know the charge. We know the mass of the electron is 9.11 into 10 raised to minus 31 kg. Simply pull out the ratio, you will get this answer. Since we are not considering the electron as wave in this chapter, so we are not going to calculate its wavelength, and effect of the electric and magnetic field is actually very easy to understand. Suppose this is a positive plate, this is a negative plate, and if a beta particle which is negative in nature, if it would want to go straight, but it will be deflected towards the positive plate because it is itself a negative one, right? Now in with respect to the magnetic field, it's little bit too difficult over here to explain over here, but still I'll try my level best. This is the north pole of one magnet, and this is the south pole of the another magnet. So the magnetic field is downwards like this, and if an electron would want to go straight, correct, then we want to find out the direction of force. So these two are my hands. This is left hand, and I am going to use Fleming's left hand rule to find out the direction of the force on the electron or the beta particle. So this is FBI. So B is the direction of magnetic field, which is downwards as per this situation, and I is the direction of current, which is in this direction because the electron is going in this direction. So opposite to that is the direction of the current, correct? So BI, so F is towards me. So basically this alpha beta particle would be pushed outside the plane of the laptop or to the plane of the paper, which I am not going to draw because I can't draw, because since this beta particle would try to come out, right? So Fleming's left hand rule is to be used when you are supposed to find the force, and right hand rule when you are supposed to find out the direction of induced current. So ionizing power is less than that of the alpha particle, and penetrating power range is actually very, very large because they are themselves very light particles, so they can go to a long distance. But the stopping resistance is about 1 meter thick of the thick lead or 5 thick aluminum sheet. They can be immediately stopped. Yes, they can do a damage more compared to the alpha particle, but less compared to the beta particles. Sorry, less compared to the gamma rays. This I had already explained you, that suppose if we keep a radioactive particle over here in the lead block, and then the alpha, beta and gamma, they simultaneously come out, the gamma radiations would go straight because they don't have any charge. Beta particles would be going in the upward direction because they themselves are negative, and alpha particles, since they are positive, they would be deflected towards the negative plate. And you could see the angle of deflection of alpha particle is less compared to the angle of deflection of beta particle, because same force, the electric field is in the downward direction. Electric field is a type of force which is, and electric field direction is from positive plate to the negative plate, right? So since there is same force acting on the beta particles as well as the alpha particles, but alpha particles are heavy, they are made up of 2 protons and 2 neutrons. So heavier particles would show less deflection. It's just like you are kicking a dog and an elephant and you would see the result, right? So the heavier particles, they actually experience less effect on giving the same amount of force, right? So the angle of deflection is very, very less compared to that of the beta particles. Please understand, when it comes to drawing, if you show these two angles as equal, these two, theta 1 and theta 2, the angle of deflection has to be different. You will lose your marks if you will show these two angles as same. This I had already explained you, and let me explain this once again. Now suppose these are the alpha, beta and gamma particles. Beta is negative, alpha is positive, and this is the north pole and south pole of one magnet. This is south and north of the another magnet. So basically magnetic field is pointing downwards. So now this is the direction of magnetic field. It is always from north to south. Consider an alpha particle. Suppose this is an alpha particle. Alpha particles are positive. So the electric current is said to be in the direction of the movement of positive charges. Correct? That is the conventional current. So conventional current flows in the direction of positive charge. So I would be going in this direction. Now you are supposed to find out the force on these particles, because any charged particle moving in a magnetic field would experience force. So that is given by that is the Lorentz force, and Fleming's left hand rule would suggest you the direction of that force. So again, like this, FBI, B is downwards, then I is like this on the alpha particle, then the force is inside the laptop. So this basically this alpha particle would be going inside the plane, like I can't draw this, but it would go inside the plane. So basically it would go towards you, correct? And then the beta particles would be coming towards me out of the plane of the laptop. That is what I had explained you, correct? Now gamma radiations are very easy to understand, and gamma radiations basically they are form of energy. And suppose if I write down XZA and I would like to put a star on it, this is a very, very highly energetic nuclei. And any energetic nuclei is going to be unstable, and they would like to lower their energy and come to the ground state. If there is excess amount of energy inside the nucleus, it is going to remain unstable. So after losing gamma radiations, it simply becomes ZA, and I'm not going to put a star over here. This is unstable. This is comparatively more stable by losing certain amount of energy. So after losing energy, this nuclei would come into the ground state. There would be no change in the atomic number or the mass number. It is because the simply energy is lost, no change in the proton and the neutron are found. So whenever there is a release of gamma radiation, the atomic number and the mass number remains the same. The nature is highly energetic radiations. Basically, these are electromagnetic radiations, EM waves, with very short wavelength. Speed is same as the speed of light, 3 into 10 raised to 8. Again, no rest mass, no charge. Specific, again, you can't find out. It is almost going to be 0, right? Because charge is 0, so the answer itself is going to be 0. The wavelength is of the order of 10 raised to minus 4 nanometers, already studied in electromagnetic waves. Since they don't have any charge, they would be passing straight when they go through electric or magnetic field, because then only the charged particles would experience force in electric and magnetic field. Ionizing power is minimum, but the penetrating power is the maximum. So basically the stopping resistance indicates, or the penetrating power indicates how much long distance it can go. So very long distance it can go in the air, right? And it can penetrate up to about 30 centimeters of thick lead sheet, right? So that's going to be a very difficult one. So, and it produces a very intense damage on the human body. So people who are exposed to radiations, they have to be they have to be taken care of very well. And the annual dosage of how much amount of the radiations that can be received by the body, that you can find it very well out in the Google, right? So this was all about the gamma radiations. This is a comparison chart of the alpha, beta as well as the gamma radiations. This was already discussed. Now I'm just putting up over here so that you can compare all of these three together. Now let's try to solve few of the numericals related to alpha, beta and gamma radiations. So here we are given plutonium 94 and 241. Now they are saying the element which is produced is also radioactive, disintegrates such that there are 8 alpha particles. So after releasing alpha particles, I'm just going to write down He2He4. 8 alpha particles are released, and again 5 beta particles are also emitted. So 5 beta particle is written like this. What is the final element produced? So simply 94 minus, now you need to multiply these two, right? So I would like to write down this very clearly once again. 94 241 minus 8 of 2He4 like this, minus 5 electron minus 1 0. So now this is 94. So 94, again this is minus. Now this is 8 to 16 and minus plus, so plus 5. So what could be this one? So 94 minus 11. So basically this is 1, 3 and 8. So 83 is the atomic number. So we have two options possible over here. And now let's figure out about the mass number. So 241, then minus, now you need to multiply 8 4s are 32, minus 32, and minus of 5 minus 0, so minus 5 into 0. So this is basically 241 minus 32. So this would be 209. Yeah, 209. So 209. So that gives A option as our correct answer. So Y 209 and 83. So basically this is bismuth. Moving on to the next question. So here Z turns into Z plus 1. So there is an increase in the atomic number. So beta minus is released. Again, Z plus 1 to Z minus 1. That means there is a reduction of 2. And atomic number decreases by 4. So definitely this is an alpha particle. Again, Z minus 1 to, there is increase in 1 atomic number. So this is plus 1s. And no change in the mass number. So this is beta minus. So what could be the correct answer? This one. Yeah, B option is the correct answer. Now, they are being said that X disintegrates into X1, then again X2, then X3. So X, suppose it is Za after losing alpha particle, so that is minus 2He4, it gives X1. So Z minus 2, A minus 4, and again there is a release of beta particle, so minus of electron which is released. So this is Z minus 2 and then plus 1, so it is going to be Z minus 1, and then it disintegrates into X2, no change in the mass number. Again there is a release of the beta particle, so minus 1 0, again it breaks into a new element, that is X3, and then we have A minus 4, and again it is Z only. So which two are the isotopes? Now isotopes are always the atomic number remains the same and mass numbers are different, right? So we would like to see that here we have Z and here we have Z. So isotopes are the elements having same atomic number, different mass number. So X and X3 is the correct answer. So B is the correct option. So now let's talk about the medicinal uses of the radioactivity. So we use cobalt in killing the cancer cells in a specified area. So cobalt 60, the radioactive isotope, because it emits gamma radiations in lot of amount. So the doctors, they actually target the gamma radiations at a specified organ where the cancer is growing, and those gamma radiations, they are very well efficient to kill those cancer cells. Of course there are lot many other things, complications that happen, but the doctors, they know the procedure, perfect procedure, as well as they know how to handle all those things very well. So the radiations coming out of the cobalt 60, most probably they are gamma radiations, they are used to kill the cancer cells, and that is known as radiotherapy, and then in form of liquid when they give it is known as chemotherapy. Then this was the first use. They are used as a weak tracers. So suppose this is a hand of a patient, right? And then through the IV fluid, IV means they inject the liquid, say suppose that is sodium chloride, right, along with some quantity of sugar. You might have seen that the doctors, they give it while the patient is under say a lot of dehydration and stuff. So along with the liquid sodium chloride, they inject liquid iodine, which is radioactive. It can be other radioactive substance too, but the doctors, they know the quantity in which it is to be put inside the body. Now they actually inject it inside the veins from which the blood is actually flowing. So since it goes inside the human body along with this sodium chloride, this radioactive substances goes, and suppose here there is a lump, like suppose there is a blockage or a tumor, right, something like that, then instead of passing through this tumor, the radioactive substances, they gather up around over here because they are unable to pass. Then if we keep a detector under it, and if we scan the whole area, then the amount of radiations coming out through this blocked part will be larger. If you put this detector somewhere over here, then these radiations which are going to be coming here out of the human body will be lesser in amount, and that is due to the radioactive substances are in motion. But when they gather up around at one particular place over there, the amount of radiations coming becomes comparatively larger, and on that basis, on that imaging basis, the doctors, they identify the problem. Since gamma radiations, they are very well efficient to kill the cancer cells, they are also used to sterilize the medical equipments, because they can kill any bacteria or viruses which are on the surface of the medical instruments. So before performing the surgery, the doctors need to be very careful that the instruments that they are going to uh, perform the surgery, those have to be very much sterilized, otherwise they may cause infections. So gamma rays, they are used to sterilize those medical equipments also. Then you are very well about the role of the alpha particles in the discovery of nucleus. So Rutherford actually carried out an experiment in which he bombarded alpha particles on gold foil. So suppose this is a gold nuclei, right, and this is an alpha particle which is positive. Now this positive alpha particle is bombarded towards the positive nuclei, and there is going to be a repulsion between both of them. And as the alpha particle reaches nearer and nearer, the repulsion becomes strong. So somewhere at this particular point, the alpha particle stops and turns back. So this distance is known as distance of closest approach, which is estimated to be the size of the nuclei or the radius of the nuclei. So hardly you can find out, you can get an estimate about what could be the possible value of the nuclear radius. Right? You learn in detail in grade 12. Then again, we are using this as tracer in the growth of the plant study. Suppose this is a plant and it has xylem tubes inside it, and then these xylem tubes, they are connected with the roots, and roots, they absorb water. So basically the water actually moves in the upward direction. We inject radioactive potassium, isotope of potassium, which is radioactive, and then along with the water it keeps on moving upwards. We can actually find out in how much time, because there are detectors again. The detectors, they will actually take up the radiations which are going to come from the radioactive potassium. So detectors, they keep on moving, so you will be able to find out in how much time the water climbs up from one area to the another in a plant. All those things can be done. Radioactive dating is also known as carbon 14 dating, and we find out the age of the organism from the remains of that person. So suppose you are going to get a bone, and we can actually find out how old this bone is by performing this procedure. Actually, you will study about this law, which is known as radioactive disintegration law, in class 12 physics in nucleus chapter, and the calculations of these carbon 14 datings are on that basis. So we are not going to discuss in detail about that, right? Then they are used as a fuel in industrial area like atomic energy. You know that uranium 92-235 are used in nuclear reactor as fuel rods. So then the fission reaction takes place, and then the energy is released. We use that energy to heat up the water. Water converts into steam, and then the electricity is produced, right? Then just remember this part. We don't have to discuss in too much of the detail. Again, the ionizing effect in luminescent science, you are very well aware about this thing, that in the gold foil experiment, this was the gold foil, right? Gold foil, and then we were bombarding, not we, actually Rutherford, he was bombarding the alpha particles, and then there was a fluorescent screen kept like this. So when these alpha particles, they got scattered, and when they hit this fluorescent screen, the light used to be emitted from here, the flashes of light. So that is known as the luminescent effect. So we use that in the making of the luminescent science, right? Then the fourth point, beta radiations are used in controlling the thickness of the paper. So suppose that there is a roller, right, and this roller is actually moving like this. You might have seen the sugar cane going through both the rollers, and then the juice comes out. In the same way, between these two rollers, there is a sheet of paper that is to be passed. And the job of the roller is to press the paper to make it uniform thickness. Now, how do we know that the thickness is uniform from this side? The rollers are working better or not? Then we keep a radioactive beta particle source over here, and just under the sheet we keep a detector. Detector is connected with the laptop. Laptop is connected with these rollers through the mechanism. Now these beta particles, when they actually travel through this small thickness of the sheet, they would take certain amount of time. Now suppose if the thickness is not proper, if the rollers are not working properly and the thickness of the paper is comparatively larger, then the beta particles would take a longer time. And then the computer or the laptop will analyze those data and will send signals to the rollers, so that rollers will work again. They will make the sheets in a comparatively better way, right? So these were some of the uses of the radioactive substances. So now let's discuss about the background radiations. So background radiations is a measure of level of ionizing radiations present in the environment at a particular location which is not due to the introduction of radiation sources. That means even if you are walking through a road and there are no visible radioactive substances around you, then also you are getting the radiations. That might be due to the radioactive substances traces present in rocks or some cosmic rays coming from the sun. They are also ionizing in nature. So basically background radiations are of ionizing radiations. They can be coming naturally from the rocks or the trees or inside from our human body also, because a human body is made up of carbon, and carbon 14 itself is radioactive. And then small traces of carbon 14 present inside our body, one in about 10 million cells, one in about 10 million atoms of carbon in our body is C14. So it emits gamma radiations in very, very small amount. That is again ionizing. So the background radiations originates from sources both natural as well as artificial. Right? Natural means you can consider the cosmic rays which are coming from the sun. They are also ionizing in nature. Man-made means medical X-rays. X-rays are also ionizing. Then fallout from nuclear weapon testing. So if there is a nuclear weapon testing site and if you go in that area that is comparatively more radioactive compared to you won't see any radioactive substances, but the background radiations are always going to come out. And again, the nuclear accidents like that took place in the Chernobyl, right? So that area itself is radioactive. Now, the internal sources mean the radium, carbon 14 and potassium in very, 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 very small amount present inside our body. They give out radiation. So our body itself is radioactive, but the thing is it gives out very, very, very little bit amount of radiations. External means the cosmic radiations coming from the sun and the solar radiation some amount, as well as the radon present in the rocks and the minerals. They are also the sources of background radiations in from the external sources, right? And these radiations are measured in sieverts. So let's move ahead. These are very, very small things. Like if we are handling the radioactive materials, what should we do? So the first thing is, while we are entering the lab, we should have appropriate clothing, right? Protective clothing. That means we should wear a lab coat with lead linings on it, because lead will not allow the radiations to go inside our body. We should be wearing gloves. We should not pick up the radioactive materials from bare hand. We should use tongs, right? Long handle tongs, so that it doesn't come in contact with our hand also. While walking on the floor, contaminated floor with radiations in it, we should be wearing shoes, right, properly. Then mostly these are the things that we take at our home, and that should be kept outside the lab. So none of the traces of the radioactive materials we are bringing at our home, right? So this was my attempt to explain radioactivity grade 10 reduced syllabus part, and I hope you might have liked it. Please subscribe to my channel if you haven't done so, and thank you for watching the video. If you have any doubts, please do comment in the comment section. Thank you a lot.